Everyone. Welcome back to the Topos Institute Colloquium. Today, we're pleased and honored to have Bartosz Milewski, who will be speaking to us about parametric profunctor preoptics. So Bartosz, whenever you're ready.
All right. Well, thank you for having me. I think this is my second time at the Topos. As usual, I mean, I have only one interest, that's optics and profunctors. So I'll be talking again about profunctors and optics. Every time you guys come up with some kind of new lens or some new kind of optics, the first thing I can think about is how to translate this into profunctor optics. And the reason I'm always interested in profunctors is that the composition of optics is much easier when you have a profunctor representation, because in profunctor representation, these optics are just regular functions. They are just functions from set to set. So you can compose them using just simple function composition, and that makes it much easier. Okay, so I'll start with stuff that probably is familiar to most of, at least to the Topos people, David and Brendan, because it's based on their papers, and it's about the use of optics to describe neural networks. So this is actually about profunctor optics, about neural networks, and about implementing this stuff in Haskell. So all this stuff is actually implemented in Haskell, and it works. I mean, I did a very simple test, but you can actually create a neural network and teach it something, and it works. So all this stuff is, I'm mostly a programmer, and the category theory is my second kind of thing. Okay, how do I switch? Okay. So in a nutshell, a neural network is something that has a forward pass and backward pass. So forward pass is when you are asking a question, right? and it's and you have a bunch of parameters that describe the neural network. So these are the weights, the biases, and all the stuff. So here they are just described by one type, P. And there is an input, S, which is sort of, it could be like a bitmap or text or something. And it produces an output, which says, this is my answer, or I recognize that particular digit or something like that. And the other part, the important part, is that you can actually teach the neural network. So this is done using the backward pass. And again, you use the same parameters, and you use the some input, but this time you are telling the neural networks, but I don't really like your answer, and I would like to change it by dA. So this is like the delta that you want to propagate backwards. So the output is, you want to adjust the output, right? You want a different output, and then neural network reacts to it by saying, okay, so I have to change the parameters by dP, and also change the input by ds. Okay, so it's telling you that actually, and this change to the input is also very important for composability. So if a neural network is a composite thing. It consists of layers of neurons, in the simplest case, right? So you want to be able to propagate the information backwards, layer by layer. So for a given layer, you will say the backward pass will tell you how to change the input, and then you can pass this change of input as a change of output for the previous layer, and so on. So in Haskell, and I'll be just like constantly switching between Haskell and category theory. In Haskell, this is just described by two functions, forward and backward, and these two functions form what is called a lens normally. But this time, this is a new type of lens called the parameterized lens, because it has this additional p parameter. So the forward pass takes P and S and produces A, and the backward pass takes PS and delta A and produces delta P and delta S, right? And you can compose these things, and there is an identity lens, so they form a category. So these could be treated as home sets in some kind of category. However, this composition and identity are not on the nodes because of associative loss and identity loss not being on the nodes. So this is actually a bicategory, and this is all described in David's paper and Brandon's paper, and also in other papers. So the category that we are interested in has as objects these pairs S and DS, and pair like ADA, and the morphism from SDS to ADA is a pair forward backward, a pair of functions. But now the question is what happens with these parameters, because both forward and backward depend on parameters which are not parts of the object. So the idea is to actually have home sets parameterized by parameters. And the formal thing to do this is that you take the parameters from a monoidal category P, because you want the composition to accumulate these parameters in a monoidal way, right? So you have to have some kind of tensor product, and you have to have a unit object, right? So a home set from A to B in a parametric category is parameterized by some object P from the category P, and when you compose them, you get another morphism that is parameterized by Q tensor P. And formally, this can be described as a locally graded category. So you can have a monoidal category V from which you take these parameters, and you create an enriched category, which is enriched over the category of co-presheaves. You look at the home object as being a functor from V to Z, right? A co-presheaf, and the composition is done using so when you enrich, you have to have a monoidal category. So a monoidal product in this category is the deconvolution. Deconvolution you can use to compose to multiply sort of two co-presheaves, right? But that's the formality, right? But in general, so the second part of optics is the actegory. So we have to define some kind of action of these parameters on our category. So an actegory is a category with an action of a monoidal category. So we have a monoidal category P, and we have an action from P cross C to C. So it's like a sort of like a group action but instead of having a group, we have a whole category, monoidal category, and it acts on our category. And this action, I will write this action as an infix blob kind of operator. And it has to satisfy some obvious coherency conditions, unit and composition, right? So when you compose two such actions, the result is the same as if you were used one action, which is a tensor product of the other actions, right? So this is the second part. And the third part is, if you look at this, you can see my, okay. So if you look at the forward and backward passes of the optic, right, you see that there is information being passed between these two passes, right? The P and S are being passed. So these are inputs to the forward pass, but they are also passed to the backward pass as PS, right? In general, this is, you can say there is some information being passed between these two passes, and it's sort of like an implementation detail, what kind of information is passed. In this case, it's P and S, but in general, it could be some other type M. Could be less information that is passed between passes. And in general, this is done by specifying optics as an existential type. In Haskell, it's called an existential type. In category theory, this is called a coend. So altogether, an optic, which is our morphism that goes from ADA to SDS and is parameterized by PDP. In general, this will be an coend with the forward and backward passes. So the forward passes goes from P times S to M times A, or P acting on S, M acting on S, using this category action. And the backward pass goes in the opposite direction from MDA to DPDS. So it updates the parameters, updates the input, and that's the backward pass. These M's are called residues. And in the simplest case, the residue is just P and S, right? But it could be anything. So the M's come from one monoidal category M, and PDP comes from another category P. And this can be directly translated to Haskell as an existential lens with a forward and backward pass, right? And this is more general than the previous the simple optics. It can be reduced to these forward backward to these two functions if the action M on A can be just a product. If this is just a product and both M and A are from the same category and this is just a product, then you can split this C into a product of two morphisms, and then you can perform the coend over M using the Yoneda reduction, and you get these two functions. So this is totally equivalent, but only in the special case, right? Okay, now this is still not, it's much more symmetric with the introduction of these residues. It's more symmetric than the previous option, but it's still not totally symmetric because you can see that PDP enter here in one way, but M enters in a different way. And if you think about this, what is a coend? A coend is sort of like taking a trace of a profunctor, right? So this is the more general thing is that you have a profunctor in which this M, the first M, is covariant, right? And the second M is in a contravariant position, right? So it's a functor from M up, from M times M up, the opposite category. And you are taking a coend over this profunctor. It's sort of like taking the diagonal part of the profunctor and summing it up, right? So a more general, and I call this preoptic, is when you actually look at it as a profunctor before doing the coend, right? So this is what I call preoptic. Preoptic is, and as you can see, it's very symmetric. The M and dm are split. It's covariant in M and contravariant in dm. And if you want to recover the optic from this or this lens from it, then you just do the diagonal thing and you equate M and dm and you do a coend. So this is a more general thing from which you can derive your optic, but it's much more symmetric. So you can think of this as a Hom set, parametrized Hom set from ADA to SDS, which is parameterized by MDM, the residues, and PDP as the parameters, right? And here's the picture that corresponds this. So the forward pass, this first Hom set, it goes from S to A, but it takes P as a parameter and outputs M as a result. And the backward pass goes the opposite direction from DA and DM. It produces DS and DP, right? And again, you can write it in Haskell as these forward and backward pass. And this is an existential form in both M, DM, and P, DP. Okay. Well, actually, it's a profunctor in MDM and PDP. Okay, and now I will introduce some notation to simplify this stuff because now we are up to 8 parameters. Okay, well, 4 parameters and 4 objects, right? So I will use bold letters for these pairs. So the category C op times C, in which all these profunctors operate, I will use bold C for this, and bold F is a morphism that goes from bold A to bold B, and bold A is a pair AA prime, bold B is a pair BB prime, and the morphism F is a pair, but it's a twisted pair. So the first one goes in the opposite direction, from B to A, and the second one goes from A prime to B prime. Okay, it's just notation. And the monoidal action of M op M on C op C, I will write it as bold M times bold A. And it's just component-wise action. It's really a pair of actions, right? So this whole preoptic, which had 8 parameters, right? And it was a pair of functions. Now in this notation has just 4 parameters and 1 function, but it's really a pair of functions going into opposite directions. And an individual morphism in this Hom object is a triple. So you pick M as a parameter, P as a parameter, and then you have a function, a morphism that goes from MA to PB, which is really a pair, a twisted pair. Okay, so in this notation, things can be calculated more quickly. So for instance, the composition, this is the important thing, that these preoptics can be composed. So they actually do form home sets in a category. They can be composed. So the composition was supposed to go from this home set times this home set to this home set, in which the parameters are accumulated using a tensor product. So both M and N are accumulated, P and Q are accumulated using tensor product. And you look at this as this is a morphism that goes from BC to from B to C, and this one goes from A to B. And when you compose, you get something that goes from A to C, but with accumulated parameters, right? And you can do this composition if you lift the first morphism, you multiply by Q, because this monoidal action is functorial, so you can lift it. You can apply it to a morphism. Instead of applying it to an object, you apply it to morphism. So you multiply this by Q, and you multiply the second one by M, right? In this here. So you get something that goes from QMB, QPC, and MNA, MQB. And you can see that these two things are almost composable if you can switch the order. So QMB is here and MQB is here. If these two actions commute, so if you can go from QMB to MQB, then these two are morphisms in C, or actually C of C, that can be composed. And they give you the composition, right? So this is the proof that the decomposition works. And there is an identity morphism that's a triple 1, 1 ID, where 1 is the unit object in M and 1 is a unit object in P. But this all works modulo associators and unitors and symmetrizers. Hence, this is a bicategory, because composition is not associative on the nose, because you have to reassociate stuff, right? And this can be rewritten in Haskell. I mean, I wouldn't believe myself doing all this stuff in category theory. I had to translate it into Haskell, because when it compiles, actually, then I know it's correct. And so here, the composition of these pre-lenses, and the important thing is here that really F3, right, the forward pass of the composition depends on forward pass of the second lens and forward pass on the first lens. And the backward pass, G, of the composition depends on the backward pass of the first lens and backward pass of the second lens. They are in the opposite order, but which means that these two passes are completely separated now, which is an interesting thing, that you can actually separate the backward and forward pass, and you can keep accumulating them separately. And only at the end, you can say, okay, now I want to take the trace of the result. Okay, and this is the identity lens written in Haskell. So all this stuff works in Haskell. Now for Tambara modules, this is my favorite part when we go into profunctors. Okay, so first let me just remind you how this stuff works for regular Tambara modules because I had to generalize them. So a Tambara module is a profunctor. So it goes. So it's a functor from C of C to set. And it sort of generalizes the idea of home functor. A home functor is also a profunctor, right? It goes from C of C to set. It's contravariant in the first object and covariant in the second object. So if you want to generalize it to optics, right, then it turns out that when the optic is your home set in your category of optics, then the home set is also a profunctor, but it's a special profunctor. It's a profunctor that actually has some additional structure map. And this structure map it's a family of natural transformations from TAB, right? So this is a profunctor in two arguments, contravariant in A, covariant in B. But there is a natural transformation for every A and B from TAB to T n times A, n times B. So it's sort of like you transform A and B using the same transformation, and there is a mapping from TAB to T and A and B, which means sort of you can imagine this as having an orbit of the action of the monoidal category where n comes from. This action of the monoidal category is an orbit in your category, and there is a mapping from elements that sit on this orbit. Well, for the profunctor. So this profunctor is not constant on the orbit, but it sort of undergoes a gauge transformation when you move along the orbit. So this alpha is sort of like a gauge transformation that moves the profunctor. Now, to describe the home set in this preoptic category, first of all, I have to separate n because this transformation alpha is a natural transformation in A, natural transformation in B, but in N, it's not. It cannot be a natural transformation because this is contravariant, this is covariant. So it is a dinatural transformation, right? But if you go to preoptics, these two things are separated. So one of them becomes N and the other becomes Dn. And now you don't have this problem of dinaturality. It's natural in one and it's natural in the other. So a triple Tambara module that describes these optics that are parametrized by M and by P is a functor from M op P times C to set. So it's like a triple profunctor, and these are all bold letter categories. So each of them is actually a pair, a product, right? So this is M op, this is P op, and this is C op. So really complicated profunctor within three different variables. But the first arguments to this profunctor, the first two arguments are these parameters. So they behave a little bit differently. So a triple Tambara module has two structured maps. The first one corresponds to this alpha. And if you look only at A, right, A transforms to NA. So it's very similar to what happened in this alpha, except that N now is a pair. So it's really acting two separate parameters, right? The other difference is that the parameters get accumulated using tensor product. So you move A to NA, but you also accumulate this N in the first parameter. And there is a second family of natural transformation, which sort of does the opposite. This time A is multiplied by Q, right? But you have a mapping from QA to A and the accumulation in the second parameter, right? So here the first parameter is accumulated, here the second parameter is accumulated. So both residues and parameters are accumulated. There are some coherence conditions, obviously. And you can define natural transformations between these triple Tambara modules. So they do form a category. So you have a category of triple Tambara modules, okay? And you might ask yourself the question, well, isn't that too much to ask for a profunctor to satisfy these, to have these two families? Isn't that too restrictive? And it turns out, no, it's actually not too restrictive. And I have a very good example of a triple Tambara module, namely the optic itself. Okay, and by the way, this is the same thing written in Haskell, in which you have, you know, T takes 4 parameters, and the action is just using Cartesian products. So these are just like Cartesian actions, right? And this is alpha and this is beta. But in the next slide, okay, you see that the preoptic is a triple Tambara module. So you take the preoptic, right? This triple MPF, right? And you fix A, and you get something that's functorial profunctor in M, profunctor in P, and profunctor in B. Okay? And this happens to be a triple Tambara module because you can define alpha for it, like a mapping from this triple to this triple, and you can do it by just lifting F by multiplying by N and doing some reassociation. And you can implement beta that goes from this triple to this triple, and you can do this by just using the associativity, right? So this is very important, that actually preoptic is a triple Tambara module, and we'll use it in a moment. Okay. So why is this important? It's important because you want to be able to represent the optics using these Tambara modules. And again, I'm first going back to just regular vanilla lenses. Okay, so a vanilla lens from ADA to SDS was defined as this coend over M, the forward pass and the backward pass, right? So this is the usual existential form of a lens. And it turns out you can replace this, it's equivalent to a Tambara representation, where you take an end over all Tambara modules. So you do the end over the Tambara category. And here you have a set. So you have a function, really a function in set from TADA to TSDS. So this function from TADA, TSDS, which is polymorphic in Tambara modules, or you take an end over Tambara modules, is completely equivalent to this length from ADA to SDS, right? And the fact that you are taking an end over all Tambara modules means that actually in implementing this function, so when you translate this to Haskell, in implementing this function, you cannot use any property of this Tambara module other than it being a profunctor and having this structure map alpha, right? And it turns out that the preoptic also has a Tambara representation. So a preoptic MPF, this triple MPF, is equivalent to an end. No, it's a triple end, but the important part is it's an end over the triple Tambara category of triple Tambara modules. And it goes from TNQA to T blah blah B, right? So just like we had here ADA to SDS, here it goes from A to B, where A is ADA and B is BDB, right? But there is also this additional characteristic accumulation of parameters using tensor product. So both of these parameters undergo accumulation using a tensor product, and there is an overall end over Q and N over the whole category P and M. Okay, and this can be shown. Okay, so this can be translated as a polymorphic function in Haskell. It's just a polymorphic function. So it says for all P1, DP1, M1, DM1, and also for all Tambara modules, triple Tambara modules T, right? And because it's a polymorphic function in Tambara modules, it means that this function here can be implemented only using alpha, beta, and lifting of functions using a profunctor, right? So going from preoptic to this triple Tambara representation, if you have an optic like this, you want to produce a mapping of Tambara modules. And you do it by composing three things, okay? First, you apply alpha to TNQA, you apply alpha. So you get M multiplied by alpha, and you accumulate Mn. Then you lift F, so you replace MA with PB. So I replace MA with PB, right? And finally, you apply beta. This is why you need both alpha and beta. Finally, you apply beta to get rid of PB. So PB goes back to B, but it gets accumulated in the second parameter. So you in all you get from TNQA to this, right? Using this composition. And the other way around, if you start from triple Tambara modules, so you have this mapping, you have this function between Tambara modules, right? Because it's a polymorphic function, it can be applied to any Tambara module, any triple Tambara module. In particular, it can be applied to preoptic, because we have just shown that preoptic is a triple Tambara module. And what kind of preoptic we have always at our disposal? The identity preoptic, right? So you have this identity preoptic 1, 1, IDMA. We apply this Tambara mapping, right? And we get an arbitrary optic. Sort of like, you know, the Yoneda trick. You apply something to an identity and you get everything, right? And these two things from Tambara to Tambara, they can be implemented in Haskell. So this one it just shows you, oh, first you apply alpha, then you lift forward, backward, and then you apply beta. So that's your to Tambara. And from Tambara, you just apply this function, this polymorphic function to identity pre-lens, and you get. So it all type checks and it works. Now you can compose these triple Tambara lenses, and they compose, as I said, by function composition. So to compose two tri-lenses F and G, you just compose these two functions, F after G, and then you have to reassociate. Okay, this is why it's not that is why it's a bicategory. So you have to use associators, but it's still simple function composition, right? And moreover, you can define also parallel composition, which is a little bit more complicated. So I'm not going to bore you with this, but there is a parallel composition. We can take two such tri-lenses using Tambara representation, and you can compose them in parallel, right? So finally, this whole apparatus can be used to actually define a neural network. And the neural network, well, first of all, you have to define a neuron, right? So a neuron contains three components. One of them is the linear lens. Linear component would just multiplies parameters by input, right? So in this case, the parameter is a vector of parameters. The input is just a vector of inputs, and it produces a number, a double number. So this D here, right? And the forward pass is just this multiplication. The backward pass using the gradient descent. So you calculate the derivatives of these two things, but this is a linear function, so this is pretty trivial stuff. So there is a linear part, and then there is the bias part, and there's the nonlinear part that you combine. And you can take this each part of and convert them to the Tambara representation. So you just apply two Tamb, right, to make it into a profunctor representation, and from that point on, you can do just regular function composition to compose them. So a neuron is a composition of linear with m inputs, then bias, which has the bias parameter, and activation, which is in this case it's like arctangent composition composition of these three, and the parameters are defined in this, right? And multi-layer perceptron, you just take a bunch of these neurons using Tambara representation. You compose them first in parallel to create a layer, and then you compose the layers one after another to create a multi-layer perceptron. And this multi-layer perceptron is also a tri-lens. Okay, so it's a Tambara representation. It's parameterized by these horrible data types, but that's, the compiler helps you figure out what data types will work. And then when you want to train this perceptron, you want to batch a bunch of perceptrons with the same parameters, but you throw a batch of inputs and compare it with a batch of outputs, right? And then you put a loss lens on top of it, which is just the squares. So here you have the squares of the differences. So this is square loss function. And you run it. And after a few iterations, it learns the input and it works. So the source code in Haskell is available on GitHub, and you can run it for yourself and see that it actually works, which is pretty surprising that actually all this stuff works. And this is so this is the link to the paper that I wrote about it. I just put it on GitHub as a PDF, and there is a link to the source code. So for people who like category theory, there is first part that is categorical. No, first part is actually Haskell, and the second part is categorical. So they are separated. So for programmers, the first part is important. For category theorists, the second part. And these are just a few papers that I read about this. So Brandon Fong and David Spivak, and of course Bruno Gavranovic wrote his PhD thesis on this stuff. And what my contribution is the definition of pre-lenses as more general than lenses and triple Tambara modules. Okay, that's it.
Thank you, Bartosz. Thank you. Thank you so much. That's very insightful. So we have time for questions now. So how we do questions here is that you can, if you're on Zoom, you can raise your hand and then I will call on you to unmute yourself. Or if you are not able to unmute yourself, you can type your question in the meeting chat and I will ask on your behalf. Okay, so I see we have a question from Kevin. You can unmute yourself.
Sure. Thanks a lot, Bartosz. It's really exciting to see some of that stuff actually get implemented. Very, very bold to imagine actually putting all that category theory into code. That's cool. I was wondering about the residues sort of started popping into the formulas in the middle of the talk at some point. And then I guess in your example implementation, the residues went back to sort of just being inputs and outputs. Do you think, is M just there because it makes the definitions of all the triple Tambara business more convenient? Or do you have any ideas about other choices of residues rather than just copy pasting inputs and outputs that might end up being useful?
Oh, yeah. Actually, in some of these simpler lenses, it turned out that the residues are simpler than just the input. Yeah, because now I mean, well, some of these components actually don't even need parameters. So like the parameters are unit objects, and some of them don't need to pass information between the passes. So it's not always just the input, right?
Okay, so even in some of the components you really implemented, because we didn't see like all three components in full detail, you sometimes throw away some of the okay.
It's also possible that you might take these parameters and maybe compress them or something like that, so like and maybe I didn't mention or stressed enough that the separation of the passes you could actually run the forward pass on the whole perceptron or even on a whole batch of perceptrons, and you can accumulate the residues. And then you can go to the backward pass and just play back these residues. It's sort of like a tape, you know, and then you can first in, first out, you know, order, and you can replay the stuff backwards. So you can even implement these two on different computers and just, you know, put it on the internet and then run it.
Cool. Thank you.
Thank you, Bartosz. Thank you, Kevin. Yeah, I had the same questions about the residues as well, but yeah, I think it's really interesting that you know, it seems to be playing maybe not just a simplification role in your in your work, but it could mean something quite interesting for neural networks, and that we should be looking at new residues for neural networks, maybe even like transformers or things like that. Yeah, so
Right.
that's interesting.
Or maybe if you are using like Bayesian networks, who knows, maybe you can just do this sampling and pass the samples as residues rather than the whole distribution.
Ah,
Yeah.
can you say that a little bit
Oh.
more? I mean, just now you were mentioning like if you have two computers, you could read back the residues. What would we expect to see from there? Like, yeah, what you mentioned that it would be interesting. Can you say something more about that?
Well, I was just thinking that, you know, you can do the training in two separate in two separate passes. Normally when you do this, there is an immediate feedback from forward to backward pass, right? Whereas here you can separate these things. So you could just record your the residues from the forward pass of the whole batch of, you know, neural networks, and then pass it to the backward pass
I see.
and replay it.
Ah, okay. Interesting. Cool. Okay. Do we have other questions from the chat? Anyone else with questions? Okay. I just actually have a really quick question. Can you go back to your slide where you show the activation function? And I guess you must have defined like the gradient of that somewhere so that everything will compose. I didn't quite catch that. So you have an activation function here, and then okay. So it's defined somewhere else in your code. Okay.
It's defined somewhere else. Yeah.
Okay. Got it. All right. Thanks. Okay. In that case, I think if there are no other questions, I'm gonna end the YouTube chat now, and we'll go back to our Zoom call. Okay. All right. We've ended the YouTube live streaming.